All right, welcome back everyone to our Physics 8B live stream. This is going to be week 4, and this week we're going to dive into capacitors. And capacitors are actually going to be a nice little break in a way because there's a few new formulas, a little bit of new material, but the new material is very straightforward, and a lot of it just reviews stuff that we've seen before. Maybe Gauss's law or computing delta V from the electric field with minus E dr that you integrate from the initial to the final location. And so a lot of the hard stuff that we did before is going to be reviewed this week. That's nice. And whatever we add that is new is actually not that complicated. So that is also nice. As you know, if you're here, the goal here is to take the topics of the week and bring to the surface the important topics, maybe address some questions that you had from the past week, and more importantly, practice on some problems that are good, let's say entry-level problems. Some of them are a little harder, but more or less I try to choose entry-level problems where we can learn how to take the information from a problem, set it up, and get the answer on some very classic type of questions that I would say you have to have seen at least once before walking into the exam room. Ideally, of course, you would do harder problems between now and then, of course, but as a starting point, if you want to kind of get your feet off the ground and you're not sure where to start when you look at a problem, these are typically good problems, and I try to select them for that. So we're going to do a very quick, I'm going to address, I got a lot of questions about electric potential, first of all, because a lot of you, don't like electric potential, and I know that. I knew it before we started, because every semester it's the same issue. It's a hard chapter to kind of wrap your head around. So I got a lot of questions. Some are worth addressing. Some are worth just punting for a little bit because I end up going over them in the problems today. So some of these I've deliberately just chosen not to include at the beginning of the video. I am going to try to clarify kind of the big picture at the beginning of the video so that we can then get to specifics within the problems that we're going to do. But well, first, of course, before we start problems, we'll do a recap of capacitors. So let's jump into it and get started. This is, you know where to find this, is on psychedemia.com. If you go to the study guides page, scroll to the bottom, you can enroll in the free course, Physics 8B live stream. No need for a credit card or anything like that. It's all free. It's one container with all of these videos, the solved problems, as well as the homework. And thank you to those of you that send me the homework assignments so I can keep it current. It's much appreciated. So before we start capacitors this week, let's talk about potential very quickly, right? Let's do a recap. Okay. Now, if the question is, why do I need electric potential? Just, again, 30,000 foot view. I need it because if I want to be able to describe why charge moves from one point to another in an electric field, I could do it with the electric force in the electric field. We've seen that before. But a lot of the time, it's going to be easier for me to do it with a difference in electric potential. And in other words, typically I'll resort to conservation of energy. Okay. But in general, I also want to know that if there's a difference in electric potential, well, there's going to be an electric field between those 2 points, pointing from high V to low V, and that a charge will move through that difference of electric potential. Now that's going to be useful, especially when we do circuits next week. But point is, the electric potential is useful because I want to be able to talk about motion of charge in terms of energy, particularly potential energy, because electric potential is electric potential energy per unit charge. Okay. Now, let's assume that we agree on that, and that this is why we need to know about electric potential. The main question then is, how do I compute electric potential? How do I know what it is? How do I know the difference between 2 points, or how do I know what it is at a given point, and then I can do it at another point and see if it's different? Well, I'm just going to kind of present it this way, for lack of a better choice. The first thing that we learned about last week, and as far as computing anything goes, was the formula VB minus VA, or you could write it V final minus V initial, it doesn't matter, is minus the integral from A to B of E dot dr. Now we talked about E dot dr and that it's E cosine theta dr and all of that, and we'll see more of it today. Now, this is a difference in electric potential, right? And we said, well, nobody calls it that because difference in electric potential is kind of a mouthful. So we call this a voltage. Okay, but the point is, it's a difference in electric potential. When you can be clever and maybe you choose a point VA that is 0 and then you get VB, which is then not the difference, but just the potential at a given point. The idea is, though, that you get delta V in general from the electric field, right? So we spent a lot of time before this chapter talking about point charges, Coulomb's law, superposition when I have multiple point charges, slice and dice to find the electric field, then Gauss's law to find the electric field if I have enough symmetry of my object that has charge. And so we spent a lot of time not only defining electric fields, but figuring out ways to compute it for different charge distributions. So we're pretty good at finding E. So it's kind of nice that if I have E, I can then get my hands on delta V, right? In other words, this is, actually I'll write it here, either by slice and dice, that would be an option, or by Gauss's law. Those are the two main methods that we have of finding the electric field. Of course, if you have a point charge, then it's even easier. It's kq over r squared. But you don't really need delta V is equal to this for a point charge because you know that V is kq over r for a point charge. So actually, maybe we present it this way. Maybe we say, okay, if we go in order of difficulty of computing V at a given point, we have V, well, no, actually, hold on. Sorry. I had an initial idea. I'm going to stick to it. Okay. So the point is, if I can find the electric field, typically with slice and dice or Gauss's law, I can then get delta V. We'll see this in one of the problems today, actually in a couple of them. All right, so it's very common, and it's important to know how to do this because there's no way you don't get a question like this on one of the exams. If it's not midterm 1, it's going to show up on the final. Okay. Now, that's if I want to find the difference, VB minus VA. And there's good reason to want to do that. Typically, we said conservation of energy last week. Now, maybe I just want to find V at a point created by a charge. Okay, now if I have a point charge, if I want to compute V directly, having a point charge is the easiest scenario, right? It's just kq over r. This is for a point charge q. So if I have 1 point charge, even if I have 10, it doesn't matter. I can just add the kq over r's for each one, and I can find V at a given point. So I'm not getting a difference, I'm getting V at a certain point. On the other hand, not everything in life is a point charge, so I can get V at a given point by slice and dice. Okay, the same slice and dice method that worked to find E, I can actually use to find V. Now, in theory, slice and dice works all the time. In practice, not every shape that has charge is going to be easy to deal with because I have to parameterize it properly, I have to integrate over the distribution, and if I have a weird shaped potato with charge and I'm trying to find V somewhere, it's going to be very painful to set up the integral. Maybe I can use a computer to help me or something like that, but if I want to be able to do it by hand, just with regular calculus with my pen, well then there's only so many options, right? So there's going to be the rod of charge, I should say the finite rod. There's going to be the semicircle. There's going to be the ring. And there's going to be the disk. Okay, those are all slice and dice problems that you will find in exams because you can do the integration by hand. I mean, probably we're going to even give you the antiderivative to do it, but you can set it up and manually parameterize the thing and compute it. Okay. By the way, when we did E for slice and dice, same thing, right? E is, by slice and dice, is for the finite rod, the semicircle, the ring, and the disk. Okay, it's just a little different because E is an electric field, so it's a vector, it has components. V is electric potential, is just a number, so it's a little nicer. But the method is the same in both cases, and the shapes that work with slice and dice are the same in both cases. And that's all in the lecture notes, if you care to have a look at those. So, with that said, that's the recap I wanted to do. I got more questions, that are very specific questions about electric potential from some of you, but I've kept them for later because it just so happened that the biggest ones just kind of show up in the problems that I had chosen to do. And it makes sense because those are the main applications and usually the main pain points when it comes to understanding potential. So I'm not gonna do any of the slice and dice, right? I did that last week. You can go back and look at the ring of charge. We did it with slice and dice. And we did talk about KQ over R for point charges, but I am gonna talk about this quite a bit, right? There's actually gonna be two problems where we use this in relation to capacitors this time, but still. And then we're gonna specifically focus on capacitors as we arrange them in parallel or in series. So I'm not so much going to focus on this today, but I did want to make the separation in your mind so that you know that there's kind of two ways of computing V. You can compute the difference, that's the left column. Typically, you already know E, and then you get delta V. The right column is directly computing V. That's either because you know for a point charge that it's KQ over R, or off we go with slice and dice, a good example of which is the ring that we covered last week. Okay, so let's get into it and let's just go over capacitors real quick. Okay, now capacitors, again, this is a nice little break because mentally capacitors are not gonna, stress our brain too hard. We've been doing some quite abstract and complicated things up until this point, but this is a very pragmatic chapter. So capacitors, first of all, let's just draw one, at least the symbol for one, which is this. Okay, so if I wanted to build a capacitor, I would take maybe two rigid pieces of metal or wire, and I would connect them to two plates. They don't have to be square, they often are, but they don't have to be. They could be rectangular or circular or whatever. And I bring the plates very close to each other, but they don't touch. And the goal is to accumulate charge on one of the plates. That's going to carry a charge Q. That is going to repel the charge from this plate. Right? The positive charges are going to leave the other plate because they get repelled. And then I'm going to get minus Q on the second plate. So that's the first very important property of capacitors, is that the plates have opposite amounts of charge. And of course, you actually have to force the capacitor to do this, because if you try to stuff a whole bunch of positive charges on the top plate, and then you're like, okay, you can do whatever you want. Well, whatever you want means we're getting out of here because we hate each other. We're going to try to get as far away as we can from each other. So you have to what's called charge a capacitor. In other words, you have to coerce it into accepting a bunch of positive charge onto its plate, either the top plate or the bottom plate. And then you have to make sure the charge is maintained. So one way to do it is to keep a battery connected that forces the capacitor to store charge. Or maybe you first connect the battery and then you open a switch so that the charge has nowhere to go. It has to stay on the capacitor plates. It's not going to go anywhere else. But the point is you have to force charge to live on a capacitor. Now you might say, well, what's the point? Okay, fair enough. Why would we invent a capacitor in the first place? Well, the goal of a capacitor is to store energy in the form of electric charge. Right? It is going to accumulate charge on the plates. In fact, it's going to create an electric field between the plates. And that energy will be available to be released in full later on. Now you might say, well, that kind of sounds like a battery. I mean, I could charge, if I charge my phone in the outlet, right, it's going to charge the battery, and then later on I can unplug my phone and the battery will supply energy to my phone. So why invent a capacitor if I have batteries? Fair enough. Batteries are very good at long-term stuff. That's actually, they take a while to charge, but that's the best application, is that you put them in a flashlight or in a cell phone, and they can power the device for a long time. They're very good at that. What they're very bad at is speed charging and discharging. So if you need a lot of energy very quickly, you won't get that from a battery. You will, however, get that from a capacitor. So capacitors can be charged very quickly, and they can also give a whole bunch of energy back very quickly by discharging. A good example, for instance, is the flash in a camera. If you needed that amount of energy that quickly, you probably charge up a capacitor. That's a little whistling that you hear when the flash is charging. If you have one of those old cameras, that's a capacitor charging up to, give you the flash that you need. In other words, a lot of energy very quickly. Okay, so that's why you would have a capacitor. Now, We mostly focus on parallel plate capacitors, but those are not the only capacitors that we are going to encounter, and we'll talk about that. Now, parallel plate capacitors are going to, first of all, have plates that are quite close to each other, and I just separated the two here so that we could see what's going on in between, but in practice they would be very close. Here I did that just to show that there's an electric field E cap that points from the positive plate to the negative plate. And as long as the plates are very close to each other, E cap between the plates will be uniform, and you can actually treat the plates as if they were infinite. It's not a perfect assumption, but it's a pretty darn good one. All right. And so E cap is going to be the electric field in between the plates in magnitude. It's going to be sigma over epsilon naught, where sigma is the charge per area of the positive plate, right? That's Q over A if we call A the area of the plates. And then if we let D here be the spacing between the plates, because I'm going to need that in a second, then we can write the following. We can write that V cap is equal to E cap times D. Now, what is V cap? V cap is the voltage across the plate. So that's kind of a new quantity of voltage, right? I mean, it's a difference in electric potential, right? It's going to be, you know, if V plus is the potential of the positive plate and V minus is the potential of the negative plate, V cap actually points from low V to high V, right? That's because it's the direction of an increase, right? Because in other words, if I want this to be 9 volts, I want it to point from low to high so that it represents plus 9 volts. If it went the other way, it would represent minus 9 volts. Now I could live with minus 9 volts, but I'd rather not. I'd rather just have positive voltages when I can, right? I don't buy a minus 9 volt battery at Albertsons. I mean, I buy a plus 9 volt battery because it's just easier. And so that's something to keep in mind, is that there's two things going on. Well, there's one thing going on, but you can look at it from two different angles. From the point of view of electric fields go from high V to low V, and they exist because there's different electric potential in two regions, and they point from high to low. If there's a different electric potential in two regions, like V plus and V minus here, you can then define the voltage across those 2 points. Typically, your voltage arrow will point from the low V to the high V, so that's a positive number, okay? So important to keep in mind, because we're going to talk about voltages a lot, especially as we move into circuits. And then the third quantity that we need to define here is capacitance. And capacitance is going to be epsilon naught A divided by D. Now, everything that I wrote here is for a parallel plate capacitor. So this is really important because we don't want to get confused between capacitors in general and the parallel plate capacitor. Okay. Now, for the parallel plate capacitor, that's the voltage, the electric field, and the capacitance of your parallel plate capacitor. In general, for all capacitors, whether they're parallel plate or not, and we'll see an example of a spherical capacitor in the problems we do today, well, whether it's a spherical capacitor, a cylindrical one, a parallel plate, whatever, however you build it, what is always true is that Q is going to be CV cap by definition of capacitance. Capacitance is actually the amount of charge per volt that you can store on the capacitor. And then the potential energy stored in the capacitor, U sub C or U cap, doesn't matter how you want to call it, is 1/2 C V cap squared. And you can write it a couple of different ways because of this formula. Right? So if you juggle things around, you can make it Q squared over 2C, which is going to be C V cap divided by 2. That's not what no, Q V cap, my bad, divided by 2. That's what I meant to write. Okay, so this is for all capacitors. That is a general definition of capacitance and its relationship to voltage and charge. And this is a general definition of the electric
potential energy stored in the capacitor. Okay, so this is for any capacitor. And we don't have to focus on the parallel plate capacitor or restrict ourselves to it, but we typically do because it's an extremely common capacitor. So these formulas, I'm not suggesting are not handy, they actually are quite handy. Oops. And it's because we very often consider that we have parallel plate capacitors. I mean, it's the most common type that you could buy at a store if you were to go buy some. All right, so not to overly simplify this, but one could argue this is all we need to know about capacitors. Not entirely true because we have to know how to arrange them in parallel or in series, and we'll talk about that in the third problem. But really, the new stuff, this is the new stuff. That's it. That's all there is to it. So again, the new stuff is not complicated, and it leans a lot on the old stuff. It's specifically finding delta V from E, and then also finding E from Gauss's law. There we go. So let's jump into the first problem. Okay, so we have this parallel plate capacitor, and we have two large plates that are connected to a 12-volt battery, and then there's a small charge here that is going to be launched in between the plates upward. That's 1/3 from the left plate, and we want to figure out how fast is it moving when it strikes one of the plates, and to tell us which plate it strikes. Okay, so well, first of all, this plate is connected to the positive terminal of the battery, so this plate is going to be positive. And this plate is connected to the negative terminal of the battery, so it's going to be negative. There we go. This is consistent with the electric field pointing from high V to low V. So you could either use the battery terminals to determine which plate is positive or negative. You could just use the electric field information and say, well, E points from high V to low V, so there's only one option for which plate is positive, which plate is negative. Now, this charge is negative, right? So this is Q, and Q is negative. And so it's going to be attracted to the positive plate. And as it travels, it's going to get deflected and presumably, assuming the plates are long enough, collide with the right plate eventually. Okay? And the question that we have is, how fast is it going when it strikes the right plate? Okay? Well, a couple of ways we could do that. We could actually do it with the electric force and kinematics because the electric field is uniform between the plates. But more likely than not, when given the choice, I'm going to do it with the conservation of energy, knowing the kinetic energy and the potential energy at the beginning and at the end, and then I'm going to be able to figure out what V final is. Okay, so this is going to be, we're going to call the potential of this plate V plus. I'm going to call the potential of this plate V minus. Okay, now by definition, remember what we just said, V capacitor is going to be V plus minus V minus. And V capacitor multiplied by, is equal to E capacitor divided by D. Right? And so, by the way, hold on, did I write that correctly? No, I'm sorry, wow. Duh. Okay, my bad. Do not do a live stream before you have coffee, is the rule. Completely messed that up, didn't I? So apologies. E obviously is volt per meter, so it is V cap over D. And if E is multiplied by distance, so I got it wrong here too. Wow, this is pretty solid. Okay, so then we have E cap is V cap, which by the way is 12 volts, just so we're clear. V cap over D. All right.
So I will fire myself after this live stream.
I'm sorry about that. That's absurd
To make that mistake. And I've seen it enough times that I ought to know better. But okay, E, the electric field is in volt per meter, so it is V cap over D. That's it. Okay, and V cap is 12 volts because if I connect the plates across the battery, what a battery does is that it maintains a constant 12 volts across its plates. Therefore, V cap is going to be 12 volts because the capacitor is directly connected to the battery. All right, now, why am I doing this? Well, I'm doing this because I need to figure out, if I'm going to write conservation of energy, what the electric potential here is relative to V plus. In other words, what is V plus minus, let's call it V initial maybe, or V zero. So let me make a copy of this, right? And I'm going to bring it down here. Okay. And then we're going to have the following notation. We're going to say that here, the electric potential is V0. Okay. Now, little V0 is speed. Let's not get confused, right? But V0 is the electric potential at the point where the particle is launched. Okay. And so if I want to write conservation of energy, I'm going to write that well, first of all, let's say that we're writing conservation of energy. Okay, always state what you're applying. Okay, I just write conservation of energy. That's to go a little quicker between you and I. On the exam, you should write by conservation of energy. You should write by Gauss's law, and so on and so forth. If you're going to use a law or a principle, you have to say what you're using, particularly if you have Borel, which is very specific about that. But in general, it's assumed that you would state what you're using. Okay, so here we have 1/2 mv0 squared. That is the kinetic energy at this point, plus q v0 is equal to the kinetic energy when it hits the right plate, 1/2 mv final squared, plus q v plus. All right. So I need to find this, which means that I really need to find V0 minus V plus, because if I rewrite this, it's going to be 1/2 of m V final squared is equal to Q V0 minus V plus 1/2 mv0 squared. All right. So I need to figure out what this is. And we talked about that last week, right? Well, how would I do that? Well, I would do that because I know the electric field in between the plates. And so, you know, if E capacitor, which is just E, is equal to V cap times D, well, I don't have enough room, hold on. Okay, so V cap over D is E cap. Then, because I know that this is 12 and I know what this is, what I conclude is it's basically constant. Right? It's a uniform electric field between the plates. That's kind of nice. It makes it easy to find V0 minus V plus. Right? And so, yes, I would start with conservation of energy, but then I would have to go to the formula V0 minus V plus is equal to minus the integral from plus to 0 of E cap dot dr. Okay, so we got to be a little bit careful there. That's going to be between here and then this plate here. Okay,
And so if this is the other plate on the left, first things first, my electric field points this way. That is E cap. Okay. Then I know that dr has to point in the direction of increasing r. So if this is dr, maybe I make this r equals 0. This is r equals d. This is then, of course, d over 3. That's what we're told. And so now I can say, well, this is minus the integral. E cap is v cap over d. Cosine of the angle between E cap and dr, which is 180, and they point in opposite directions, so the angle between the two is 180, dr. And then plus here refers to this plate, so this is going to be from D. 2, 0 refers to this location, that is d over 3. And so maybe I just lower this so that we can see this properly. This is going to be d over 3. All right. Now cosine 180 is equal to minus 1. That's going to kill the minus out front. So I'm going to get d over 3 d v cap over d times dr. And because v cap over d is a constant, I can pull it out. If I integrate dr, I just get r. And then I evaluate between the bounds. And so that's going to be v cap over d is d over 3 minus d. That's minus 2/3 of d, and then the d cancels, so it's minus 2/3 of v cap. Okay. Now maybe I quickly check that the negative makes sense. Okay, if you look at this, v0 and v plus is going to be more positive than v0, right? Because as I go from left to right, v increases. And so it makes sense that if I do v0 minus v plus, I get a negative number. In particular, I get minus 2/3 of v cap. All right. So then if we resume our conservation of energy, we can say that 1/2 mv final squared is equal to, well, q times this delta v. So minus 2q v cap over 3 plus 1/2 mv0 squared. Okay, if we multiply by 2, divide by m, we get v final squared is equal to minus 4q v cap divided by 3m plus v0 squared. We just keep the positive root then to get v final, and that's going to be v final. And we can do better than that because we have all the values we need to compute this thing. Okay, so careful, remember that q is negative, right? So this is actually a positive quantity, which makes sense. V final should be bigger than v0 because you're speeding up as you move toward the right plate. All right, so this is 4 multiplied by q is minus 3. V cap is 12 because it's the voltage of the battery. 3 times 2, that's for the mass m, and then plus v0 is 1 meter per second. And so this is going to be, well, 3 goes away, the minus goes away. I get 2 upstairs times 12 is 24 plus 1 is 25, so I get root 25, how convenient, which is 5 meters per second. All right, so short of embarrassing myself to no end because I messed up my formula, hopefully the rest makes sense. You know, as my undergrad physics teacher said, bless her heart, you're allowed to make mistakes in physics, you're just not allowed to not spot them.
So that was my bad. Wasn't careful. But hopefully this makes sense, and this should, in theory, bring you back to what we did last week. Right? We said conservation of energy is a big motivation in the electric potential chapter. Particularly, we want to be able to compute these differences here, V plus minus V minus, or V0 minus V plus, or whatever it is, and from the electric field, because we know what the electric field is. Now, it turns out for a parallel plate capacitor, electric field is quite nice. It's constant. It's a uniform electric field. So it's very easy to do the calculus and to get the electric potential difference. Now, it's a little bit harder if you don't have a nice electric field that's constant and uniform, but it's still doable, and we're going to do that in this next problem here. So the problem we just did is a classic problem in the sense that if I'm going to have a charge moving through an electric field, not only is it likely that I will use conservation of energy, but one way to do it is to put two plates close to each other to create a nice electric field and then let the particle do whatever it does. And there's a bunch of applications of that, and we'll talk about those maybe a little bit later, like the mass spectrometer or whatever. But that's for magnetism. So anyway, it's a classic type of problem. Now, another classic type of problem is to say, well, look, we went through the parallel plate capacitor in detail in lecture, and we did the derivation, and the derivation had a certain pattern to it. And it turns out this pattern can be replicated for either a cylindrical capacitor, very classic, it's been on multiple exams, or a spherical capacitor, very classic, has been on multiple exams. Now, it is not our responsibility to figure out how you would build such a thing, right? Especially if there's air in the middle here. You're like, well, this is not something, you can't build it, right? It's not possible. It's like, fair enough, I got you. Yes, you're right. You could imagine that you put some insulating material here in between, call it cork, call it newspaper, it doesn't matter, right? So you are not responsible for the engineering of this thing. You're not trying to build it. You're just rolling with the fact that it is what it is. This is a spherical capacitor. We're going to take the pattern from the parallel plate capacitor derivation to get its capacitance. That's the only goal. And the pattern was the following. Find the electric field between the plates, here between the two spheres, then find the voltage across the plates, and then say C is Q over V by definition. And so then you get capacitance. All right, that's how you got epsilon A over D for the parallel plate capacitor. All right, so find the electric field between the capacitor plates, all right, between R1 and R2. Well, that sounds like something I know how to do. I mean, after all, this thing has the right symmetry to apply Gauss's law, right? And so this is going to be the sphere in the center here. This is R1 and this is R2. Q minus Q. And I want the electric field between the plates. Okay, and I know that from the symmetry, it's going to be a radially outward electric field. I'm going to go ahead and call it E cap directly because it's going to be the electric field of this capacitor. And if I want to figure out what it is, I choose a Gaussian sphere that lives in between the two spheres with the radius little r, and an outward normal, dA, that is along the electric field everywhere. Right, so we've done this a million times. This is Gauss's law for a sphere of charge. Okay, so by Gauss's, well, not by Gauss's law yet. First, let's compute the electric flux. Flux is outward, so it's positive. It's going to be E cap multiplied by the surface area of the Gaussian sphere. And then Q enclosed over epsilon naught is the amount of charge enclosed, which is just Q. And we divide that by epsilon naught. Okay, hopefully we all agree. The only amount of charge that lives inside this Gaussian sphere is Q. All right. And so by Gauss's law, and you should always say by Gauss's law if you're going to apply it, the flux, E cap 4 pi r squared, is equal to Q over epsilon naught. And of course, at this point, hopefully nobody is surprised that we find the same electric field that a point charge would create, because once you're in the gap between the two,
that sphere in the center sure as heck looks like a point charge. All right. So that is E cap. Cool. All right, so it's the electric field between the plates. It's radially outward if I need to specify that. Sorry, this is bothering me. There we go. It's a little bit better. Okay, there we go. So that is the electric field in between the plates. That's the first step. Okay. Then we're going to find the voltage across the plates. We're going to do what we did before. We're going to find delta V. Right? It's going to be, if this has a potential V minus and this has a potential V plus, just because I want a positive number, I'm going to compute V plus minus V minus. If you compute V minus minus V plus, it's cool. Just take the absolute value at the end because you're going to plug it into capacitance and you want capacitance to be positive anyway. So let's find the voltage across the plates. And so I'm going to exaggerate this drawing so that we can see what's going on, right? So I'm going to make the sphere in the center quite small because I don't really need it, right? I need to see the electric field though. That's the most important part. So my electric field is radially outward. This is E cap, and I know its magnitude. All right. And if this here is V plus, and right here I have, let me move this, V minus, oh come on, V minus, then I want to compute V plus minus V minus, right? This difference in potential is V cap. It's the voltage across the capacitor plates. Okay, well, it's going to be minus the integral from minus to plus of E cap dot dr. All right, dr is radially outward, like this. And just as a reminder, I mean, this is a radius R1, and this is a radius R2. So this is going to be minus the integral E cap dot dr is, by definition, E cap in magnitude, cosine theta, where theta is the angle between these two vectors, times dr. Now the angle between these two vectors here is not 180 like before, it's just 0. They point in the same direction, right? So there's no angle in between them. And this is going to be Q over 4 pi epsilon naught r squared, cosine of 0, which is 1, dr. Okay, and then minus refers to V minus, and so that is actually R2. Plus refers to V plus, and that is corresponding to R1. So those are my bounds. All right. Okay, so now I have cosine of 0 is 1, minus, if I integrate 1 over r squared, I get minus 1 over r. So this is going to be minus q over 4 pi epsilon naught r to be evaluated between r2 and r1. The minus signs cancel each other out, right? If you absorb this inside, it's going to cancel that minus. And so I'm just going to get q divided by 4 pi epsilon naught r1 minus q divided by, oh come on, 4 pi epsilon naught r2, which is a positive quantity because r1 is smaller than r2, meaning that this denominator is smaller than this one and the first fraction is bigger than the second, so the difference is positive. All right, so that is V cap. Okay. Now you can leave it like that. You would probably find that just because we know what's coming next, finding C, GSIs or answer keys would kind of get it to have the same denominator, right? So you don't have to, this is the right answer still, but if it were up to me, I would do this. I would say V cap is Q over 4 pi epsilon naught R1 R2 times R2 minus R1. That would be what I would do right now, just because, again, I know that I'm going to need V cap later, and so I might as well get it in the most condensed form possible. Okay. So
again, we're following the same pattern. Found E using Gauss's law, found V with the delta V formula, or V cap with the delta V formula, and then determine the capacitance of the capacitor is very straightforward.
By definition of capacitance, it is Q, the charge on the positive plate, divided by V cap. So it is Q divided by this whole thing, Q R2 minus R1 over 4 pi epsilon naught R1 R2. What you should find is that charge goes away, right? So it's not a function of charge. You get 4 pi epsilon naught R1 R2 divided by R2 minus R1. And that is a remarkable property of capacitance, which is that capacitance, which measures the ability of a capacitor to store charge, in particular, it tells you how much charge you can store per volt across the capacitor plates, C is independent of the amount of charge already existing on the plates. So as you build up charge on the plates, it does not change your ability to store charge. Your ability is your ability. It is in fact only a function of the shape and size of your capacitor, which is why it's only a function of R1 and R2 effectively. Now, yes, of course, there's epsilon naught, fair enough. And if we had a dielectric in between the plates, that would change it. That's all true. But as far as the fundamental property of capacitance being independent of charge, really the only thing that dictates what your capacitance is going to be is the shape and size of it. And you could mitigate that with a dielectric if you want, but that's an important property of capacitance to keep in mind. So, super classic problem. In the same way you could do the cylindrical capacitor, because again, if you have two concentric cylinders, like you have two concentric spheres here, Gauss's law applies, so you find E, find delta V, find the capacitance because it's Q over V. So parallel plate capacitor, cylindrical plate capacitor, and spherical capacitor are all classic exam questions. Do not walk into the exam room without knowing how to apply this method to find the capacitance for each one. Like that would just be, it would be sad. All right, so continuing on, let's change our focus a little bit. This has been kind of zooming in on capacitors and like what happens in between the plates and what's the voltage across the plates, the electric field, and what's the capacitance and whatever. We're going to try to zoom out a bit and say, well, if I go buy capacitors at Radio Shack, although Radio Shack doesn't exist anymore, RIP. If I go buy capacitors online and I get them in the mail, I can arrange them in a circuit to achieve a certain goal, and whatever that is, whether it's just storing charge or doing something more complicated. But then I'm not really focusing on what happens, what the capacitor looks like, what are the dimensions, what happens inside. I'm just focusing on the macro behavior of daisy chaining a couple of capacitors together or arranging them maybe like this arrangement or something similar. So this is more of a circuit kind of problem, and you're going to see that next week we're going to really move into circuits and we're going to see stuff that looks like that. And ultimately we're going to mix stuff around. We're going to have capacitors and resistors and whatever. But let's assume you have four capacitors, two capacitors C1 and two capacitors C2. And now let's just highlight what we know here. We know C2 is 3 farad, right? And the battery supplies 10 volts. And the idea is that you have C1 and C2, two of each, and you arrange them in this square shape. That's how you connect them to each other. Now, in general, if you connect a bunch of resistors like this, they behave like a single, if I said resistor, I meant capacitors. If you connect a bunch of capacitors like this in the square pattern, the behavior of this whole thing is equivalent to one single equivalent capacitor. So you can replace all four with one single equivalent capacitor, okay, depending on how they're connected. So that's an interesting
property. I mean, it's not obvious that you would get that. By combining capacitors, they just end up behaving like either a better or a worse capacitor, depending on how you connect them together. So before we dive into the problem, let's just do a quick recap, because these again are very simple formulas that are part of this chapter, but we should just make sure that we review them before we start using them. I don't want to start using stuff and you then have no clue where it came from. Okay, so here's one capacitor, and I'm going to take it, I'm going to duplicate it, and let's say I have 3 of them. Now usually we do it with just 2, but my point is to show you here that 2 or more, the formula generalizes for the equivalent capacitor. So if this is C1, C2, and C3, these are equivalent to one single capacitor with an equivalent capacitor, C equivalent. Okay, so in other words, instead of buying 3, you could buy just 1 with the right value of C equivalent, and if you connected this to a battery or this to a battery, the battery would not know the difference. Couldn't be able to tell you whether there's 3 capacitors or just 1. Be like, well, I don't know. Here you go. This thing behaves as if it were just one equivalent capacitor. So it's nice because if you have complicated, connection or arrays or connections of capacitors together, you can simplify them down to one equivalent capacitor most of the time. Okay, now these capacitors here, C1, C2, and C3, are connected in parallel. Now, of course, you're like, well, no, duh, no shit, they're in parallel because, well, they're parallel to each other. Okay, yeah, they do. They look parallel. That's not really why we call it that. Call it parallel because you could argue that's because these 2 wires are in parallel. In fact, that might not be the best way to think about it either. Capacitors will be connected in parallel if they're connected the same way across 2 wires. Let's say this is the blue wire, this is the red wire. All 3 capacitors are connected the same way. The top of C1, C2, C3 is connected to the blue wire. The bottom of C1, C2, C3 is connected to the red wire. That means that they're in parallel. Now, yes, when we draw them, we tend to draw them so that they look parallel to each other. Now, the truth is, though, if I wanted to draw C3 like this, C2 like this, and C1 like this, it would be no different because they're still connected the same way across the 2 wires, and they're definitely not parallel. But anyway, as long as we agree that when they're connected like this, they're connected in parallel, so that if this is the voltage between the 2 wires, all capacitors have the same voltage, so capacitors in parallel share the same voltage, then they're going to be equivalent to one single equivalent capacitor, and C equivalent is going to be very easy to get. It's just going to be the sum C1 plus C2 plus C3, and so on. If you had 4, it would be plus C4, plus C5. If you have 5, etc., etc., it generalizes. Right? Now that's for capacitors in parallel. Now you do not have to connect capacitors in parallel. You could buy capacitors and you could daisy chain them. Right? You could connect one after the other, like this. Okay. In which case, you could no longer argue that they're in parallel. They're definitely not. And the reason they're not is because they're no longer connected the same way across these 2 wires. If this is the red wire from earlier, and this is the blue wire from earlier, then it is not the case that they're all connected the same way, right? In fact, this one has the left plate connected to the blue wire, this one has the right plate connected to the red wire, and this one is just connected in between the 2 capacitors. So yes, it's C1, C2, and C3, but now they're in series. Now in series is usually pretty easy to spot because you daisy chain them, right? You connect them one after the other. There's no option. There's only one way through here. It's through all 3 capacitors because they're one after the other. So usually in series is pretty easy to spot. Now if they're in series, they're not going to share the same voltage, but they are going to share the same current. In fact, they're also going to share the same charge. Now, current doesn't mean much for us yet. Wait till next week. But capacitors in series will carry the same amount of charge. Now, there will also be equivalent to a single equivalent capacitor with a capacitance C equivalent that is given by 1 over C equivalent is going to be 1 over C1 plus 1 over C2 plus 1 over C3. All right. And of course, it generalizes. If you have 4, it's plus 1 over C4, and so on and so forth. Okay. So that's just a quick recap. Oops. So hold on. There you go. Before we dive into the problem, but you have to be able to recognize when capacitors are in series or in parallel, and then combine them into one equivalent capacitor because it's going to make your life easier. All right, so let's see how this works here. Because here we have two configurations. We take this arrangement that you've made, and we either connect the battery across here and here, or across here and here, which is not the same thing, it turns out. And we're told that C equivalent for A times C equivalent for B is equal to 6, and F squared is farad squared. It's the unit squared. Right? So the F doesn't mean anything other than the unit. And so the product of the two equivalent capacitances is 6 farad squared. Can we figure out what C equivalent B is, or no, I'm sorry, what C1 is rather, because we know C2. And of course, to do that, we will find C equivalent A and C equivalent B. Okay, so let's start with configuration A, and then we'll do configuration B. We're going to try to find C1. Okay, so configuration A. Okay, now first things first, we're trying to find the equivalent capacitor, right? So it means we have to figure out whether these are in parallel or in series. Now, the only reason we would draw capacitors slanted like that is to confuse you. This is psychological warfare. That's all it is. Right? It's to confuse you on the exam, to see if you can, bring this back to something that you know, or just deal with the fact that they're slanted. It doesn't truly matter, but it is intimidating if you've never seen that before. Right? If it's always been either vertical or horizontal capacitors, and you walk in and you see this, you're like, oh shit. All right. Now the truth is, I can redraw this thing. Right? Now, if I were to redraw this, I would do this. I would draw it like that, and let me draw one capacitor, and then I'll make a few copies of it. I would redraw it like this. Okay, and I'd say, okay, was this what we have on the left is the same thing as this. It's the exact same thing. All right, so this is C1, and this is C2, and this is C1, and this is C2. There we go. Okay. No difference. All right. So with that point made, let me move this up a little bit. With that point made, I can now say, well, let me start with the simplest combination of two capacitors that I for sure can tell whether they're in parallel or in series. Okay, C1 and C2 are one after the other. They're absolutely in series. Same thing here for that matter. All right, so I'm going to say C1 in series with C2. Okay, now I always want to say how they're arranged before I write the formula, because now I can say, okay, well, let's call C12 the equivalent capacitance. 1 over C12 is 1 over C1 plus 1 over C2, okay, which is C1 plus C2 divided by C1, C2. Okay, and now don't make the mistake 25% of students make when they do this on the exam. They forget to flip it. We don't want 1 over C12. We want C12. So C12 is going to be C1, C2 divided by C1 plus C2. Okay. So now we're claiming that this thing here is equivalent to
the following. It's equivalent to the two branches, right? Hold on, let me move this. The two branches on the left and on the right are going to be reduced to their equivalent capacitor. Oh, come on, wow. The struggle is real. Come on. There we go. Oh, man, oh, man. All right, so then it is as if I had C12 here and C12. Okay, in other words, in terms of behavior, there is no difference between this and between this, so long as C12 is equal to this. Okay, but so now I can say, guess what? Let me find the combination of two capacitors that I know for sure is either in series or in parallel. Well, these two are in parallel, right? Remember, they're connected the same way across these two wires, right? The top of C12 on both sides is connected to the blue wire, bottom is connected to the red wire. They're in parallel. Okay, well that's easy. Parallel capacitors are pretty easy to deal with. So C12 is in parallel with C12. And once I combine these two into one single equivalent capacitor, well, I'm done because I've taken my arrangement of 4 and I've combined it down to one equivalent capacitor. So the capacitor that I'm going to get is going to have a capacitance C equivalent. I'm going to call it C equivalent A for configuration A. And it's going to be C12 plus C12. It's going to be 2 C1 C2 divided by C1 plus C2. And I'm just going to box it even though nobody asked me to really find that. But I'm going to need it later to find the capacitance C2, right, or C1, whichever one we don't know. Okay, so that's for configuration A. All right, we took configuration A and we simplified it down to one single equivalent capacitor with an equivalent capacitance, C equivalent A. Okay, let's do the same thing with configuration B. Now, here we go again, right? Configuration B has slanted capacitors. That is only to scare you, okay? So we are going to redraw this arrangement and say that it is the same as this, right? It is the same as having C1 here, followed by C1 again, and then down here, C2 followed by C2. So it is the same thing to draw it like this or like this, as long as this is C1 and C1 and this is C2 and C2. Okay? Now, of course, if I start by trying to find the pair of two capacitors for which I absolutely know whether they're in parallel or in series, I'm going to argue that C1 is in series with C1, C2 is in series with C2. Right? So I'm going to combine those two at the top and the two at the bottom into one equivalent capacitor. Okay? So I'm going to get something different, in other words, than what I got with configuration A, but I kind of expected that. So C1 is in series with C1. Okay, so the equivalent capacitor, let's call it C11, is going to satisfy 1 over C11 is 1 over C1 plus 1 over C1, which is 2 over C1, and we don't forget to flip this. We get C11 is C1 over 2. Okay, for that matter, okay, C2 is in series with C2. Okay, so I'm not going to redo everything. Right? If I show my work once, I can leverage it and say, well, C22 is going to be C2 over 2 with the exact same logic, right? Because I showed my work fully once. This is exact, just a copy-paste, basically. I would just be changing ones into twos. That's all I'd be doing. Okay, so then this thing here is going to be equivalent to the following arrangement. It is as if I had C11 here and C22 here, connected like this and like this. Same thing. All right. Now if I look at C11 and C22, hopefully I can convince myself that they're in parallel. They're in parallel because they're connected the same way across the blue and the red wires here. Right? Left of C11 and left of C22 are connected to blue. Right plate of both are connected to red. Okay? So then I would say C11 and C22 are in parallel. And once I combine them, I will have one single equivalent capacitor. So I'm just going to call it capacitance C equivalent B for configuration B. It's quite easy because when capacitors are in parallel, we just add the capacitances, C11 plus C22. All right, well that's going to be C1 over 2 plus C2 over 2. In other words, that's C1 plus C2 divided by 2. Okay, and I want to solve for C1. And I am told by the problem that C equivalent A multiplied by C equivalent B is equal to 6 farad squared. Okay, well, C equivalent A times C equivalent B, I know what it is, right? C equivalent A is 2C1C2 over C1 plus C2 multiplied by C equivalent B is this, right? So this simplifies nicely. 2 goes away, C1, C2 goes away, and I just get C1 times C2. Now I'm told that C2 is equal to 3 farad, and so if I want to solve for C1, C1 is just going to be C equivalent A times C equivalent B divided by C2. That is going to be 6 divided by C2 is 3. So I'm going to get 2 farad for C1. All right. So here's a classic example of a problem where we're looking at capacitors more from a macro point of view and how do they behave if we put them in a circuit, in particular if we put multiple ones in a circuit. And the reason why, I don't know if that's the right way to start that sentence. This type of problem is a very classic problem, let me say it that way. And so my reasoning for including it is that as soon as this week, so as soon as this capacitors chapter, we need to be able to combine capacitors in series and in parallel and find C equivalent, right? We need to also be able to figure out what happens if we connect capacitors together, but then maybe we take one of them and we separate the plates or we bring the plates together. Very classic. That's a lot of old exams have problems like that. Or maybe we put a dielectric slab in between one of them and not the other. What happens? So those are harder problems than this one, but they kind of have the same flavor, and you first have to be comfortable with parallel and series and knowing how to deal with capacitors in the context of a circuit. And of course, this is going to go one step further next week when we start talking about resistors, and resistors can also be combined in parallel and in series and so on and so forth. And so then we're going to develop more rules to study circuits and to figure out, how to find the brightness of a bulb or how much power is dissipated by a resistor, things like that, which again is also a very practical chapter, all things considered. So what I mean by that is the three first chapters, right? Electric fields, Gauss's law, and electric potential. They all go together. They're a coherent whole, but they're very abstract in comparison to circuits and capacitors. So circuits and capacitors are nice just because right before midterm 1, that's kind of a nice slowdown in the pace. And they also help you review previous stuff. And it takes a lot less time to be very good at capacitors and circuits than it does to be good at the older stuff. Okay, but the older stuff, I'm not saying it's not going to be on the exam. It's obviously definitely going to be on the exam.
usually out of 4 problems, one of them is circuits or capacitors. The other 3 is the other stuff. So don't neglect that and spend some time on that. But, it's nice to know that you're not going to have to put in the same amount of effort for capacitors and resistors as you did for the earlier stuff, because it's typically a bit more straightforward and systematic how you would solve these types of problems. So anyway, hopefully that helps clarify this chapter on capacitors and what you might expect in terms of practice problems. If you need help with Physics 8B, I will shamelessly plug myself. Please feel free to reach out. You can sign up for the study guides online. You can sign up for the masterclass if you want unlimited tutoring. If you want just regular good old tutoring, you can contact me. I do that too. You don't have to. You can just use the free resources. I'm happy to provide them. I just say this because as we get closer to midterms, spots fill up, and when spots are full, that's it. I can't make the weekday longer. So anyway, thanks as always. Thanks for watching. Thank you for your questions. I hope that for those of you, well, I've addressed your questions already, but for those of you who had questions that got addressed by these problems, at least I think so, hopefully that really helps solidify why you were confused about computing delta V in that case, or confused about how do I recognize that these are first in series, C1 and C1 and C2 and C2. Why do I not say that they're first in parallel like that? Okay, well, again, it's because you start with the combination of 2 capacitors for which there is no doubt, right? And so if you say that these are in parallel, well, yes, the 2 arrangements, top and bottom, are in parallel. I'll agree with you. But that involves 4 capacitors at first, right? So take 2. These 2 for sure are in series. Same for these 2. Boil them down to 2. Okay, now these 2. Well, these 2 are in parallel. Okay, and you keep going, right? So there's only 2 steps for this one, but you could have a more complicated network, and you just keep going step by taking the pair of capacitors that you know for sure is either in series or in parallel, which is a great question. I mean, it's one of the hardest things in circuits is to unambiguously be able to tell whether components are in series or in parallel. And it's something, I mean, I get questions all the way to right before the final on that every semester, because it doesn't look complicated, but when you sit down and you have to face it, it's easy to confuse yourself or to not realize how you systematically go about it. So hopefully that helps. Just take the 2 that you know for sure are either in series and parallel, reduce them into 1, then do it again, and as you go, you just find the 2 that are either in series or parallel, and you keep repeating it, and you should be able to get down to 1 single equivalent capacitor. All right, that should be all for this week. Again, thanks for watching, appreciate it. Thanks for sharing also, appreciate that too. If you have any questions, feel free to reach out. I'm always happy to, help out in terms of, what to study, how to study. Anything that I said that wasn't clear during these live streams, or, part of the homework that if you find a typo in the homework, it's possible, let me know. And I always appreciate the feedback. So with all that said, hope you have a great weekend. I will see you next week. We'll be doing circuits so that we're ready for midterm 1 and we've covered everything we need to cover before it comes around. All right, have a good one. Take care.